I'm very happy and honored to receive this Acheson Award. So this time, I hope to introduce my total and especially the recent research works. So, but a target of my talk is just how to achieve the industrial innovation from the basic researches. So I just show the three items: magnetic recording field, batteries, and biotips. And okay, this is just the content. But the first time, I'm just show you the concept of the R&D strategy on that. Okay, the electro nanotechnologies. Then the recently I got, but it's year is 2008 to 2012. At that time, $1 million or each year and continue the 5 years is just offered to from the government to create the establishment of electrochemical device engineering. So at that time, I proposed three-dimension design for the energy devices. Always, energy devices need the power and also the large charges. So the three-dimension of the electrode is very important thing. And also, the two-dimension design for the sensing devices. This is the sensors. Usually the sensors should be going to the smaller, and the surface is so important to, so the two-dimension is so important things. And so just extra one is the zero dimension, which is another particles. But this time I cut this one. But anyway, I introduced the two types of the dimensions, how to go to the devices and how to go to the industrialization. So my work is from the beginning, I worked for the batteries and also the electronics devices. And recently we started the sensing and also the magnetic recording devices is also started at the younger food. And the first time I will introduce the magnetic recording devices and also electronic devices are a little bit cut. And this is the practical use in the electronic devices and the batteries from our basic researches. And several one is a collaboration from the industry in Japan. And the most good chances to the big success is the hard disk at that time, the magnetic head. But before that, we working for the magnetic media. But at that time, I just used the cobalt, iron, nickel, soft materials, collaboration together over the energy. And finally, the Fujitsu bought that patent, and fortunately, I got a big patent money. But I would like to introduce this one, and also recently the micro pH sensors. This is the first study, the collaboration with Horrible, but recently I collaborated with many companies, and also the batteries I started a long time ago, but the lithium-ion batteries checkers is now the collaborator Panasonic, Toyota, and the other device makers. So I would like to three of them to show you. The first one is the magnetic materials for the hard disk, and especially the head. And at that time, usually it should going to the smaller. Yeah, the Ruby is invented such kind of thin film head, and the trend is coming to the thin film head, and with mixing the MIG head and the AMR and the GMR. And around that point, and the high BS material is required. But So the reason is to downsizing. So at that time, we started the collaboration together with the NEC. And this is the final result of the ultra small head with a high BS. When creating high BS, it decreasing so smaller. Still, such kind of the shape is using a little bit changing, but still this type is using for the perpendicular recording too. The shape is this one, and Ruby is inventing to the same thickness, but the shape is so blended, but always the same thickness. So spattering is a very tough work, but electro-deposition is possible. So this key is just framework plating. So the long time ago, he created we followed it, and this one is just example of the cobalt iron nickel materials at that time. At that time, idea is how to create the high BS. Usually, the grain size reduction is effective to control the coercivity, but the coercivity is always bigger. So we need less than 1 Elsted or nearly the 1 Elsted. So the idea is how to reduce the grain sizes. So the first idea is the additional additives. Then we use the saccharine and the cyurea to decrease the sizes. So we succeeded this one, but the NEC real industrialization is a claim to, because the saccharine and the cyurea, when using it, so the additives adsorption is just stronger. So very strong adsorption, and sometimes finish the process, and the next times it cannot work. So they claim to take off this one. Usually the additive is very important thing to making a small size plating, but this time the thickness is smaller. So, and the stress might be the smaller if utilizing without the additives. And also, the next idea is just utilize of the FCC, BCC phase boundaries. Maybe this is just the first ideas to discussing the student. And if the FCC and the BCC is grown up, maybe the particle is very tough work to grow up. So this is the next idea. So then finally, we found out this is the nickel, iron, cobalt, 3 elements items. But the first one is, IBM is 80 power molecules here, and 45 power molecules is coming too. The BS is just 1 Tesla to going to the 1.6 or Tesla or something. So then the largest BS is around here, 2.4 Tesla is the biggest one. But every company is trying to these places, but never find out the particle size at the lower coercivity. So idea is just, so additive is find out around here, but the NEC refused it. So we just trying to around here, because this is just borders of the FCC and the BCC. And also the lambda is where is I've forgotten to. Lambda is just the stress. Magnetic stress is going to the lower places. So fortunately, we found these areas. The BS is nearly the 2 Tesla. And how about the HC, or the coercivity? So fortunately, it becomes less than 2 Elsted. So we just ship the patent. But this idea is a new one, so no one have a patent around here. So the less than 1 year, immediately the patent is coming out, and also the US patent is coming out. So it's so lucky for us at that time. But recently also we found out around this one. But anyway, so at that time I surprised, okay, total market in the magnetic disk field is so large amount of it. So the total market is so bigger, and also the patent charge is coming to suddenly so bigger, and also the high BS coercivity is the collaboration of the energy is maybe that cannot come to the patent amount so well, but fortunately or unfortunately, I don't know, but energy is just the top of the energy stop to creating the magnetic devices. Just follow to the IBM at that they decided. So the top of the magnetic head people is just worried about to. So this, but head people is just, at that time, senior manager is just told me, okay, this is one of the best results, so should sell to some companies. But he tried to the many companies, but finally, he tried to the Fujitsu. But the Fujitsu, and if the IBM is buy it, it's no problem. Usually the Japan companies, I'm thinking IBM is the so biggest, so IBM technology is easier to buy it. But the Fujitsu is just thinking, okay, NEC is just the same size as to, so never buy it. So that is a big problem. So, but fortunately, the head of the magnetics in the Fujitsu is my good friend. Okay, this is ours, not NEC. So they contract together with the Waseda, and then the income or the patent is shared to the NEC from the Waseda. It's really lucky. So the $2 million each year, continued several years, it comes to us. So this is so lucky at that time. Anyway, this is just lighting we transferred all our technology to the other companies through TLO, the Waseda. This is the first success in our university a long time ago. Then the next trial is, at that time, we trying longitudinal and perpendicular coming, and from at that time, there are several items, but now the 20 terabits per square inch is Mama and Tama. From the plating side, I just proposed to the bit patterned one. So the one of the result recent one, but this is just plating with a bit one. This is a pattern of the 100 nanometers, less than 100 nanometers, but deposition nanoparticle, the platinum and iron nanoparticle is just dispersed, and hit it, this becomes a bigger data. But anyway, this is still the continuously. And the next challenges of the quicker. And the batteries and the fuel cells. But I cut off the fuel cells just to show you the batteries, or especially the lithium batteries. When I was a president, I just showing the columns of Pennington corners, and at that time, just showing these pictures. These pictures is just showing the battery is just growing up over the capacities. So the recycling plant of the batteries becomes so important things at that time. So then how to make recycling. So maintenance free is a very important thing, and also analysis without destruction is also the very important to check the health condition of the battery. So we focus on these items. But fortunately, I'm familiar to the impedance, electrochemical impedance spectroscopy, and this can be applied to check the battery degradations without destruction. So the reason is, this is Mark Orland data, and from the 1981 or 82, I just starting the Fourier transformation technologies, because this technology is just learned from the Georgetown University Robert Dreby's labs. I spent 2 years in postdoc at that time. So then after his postdoc period, I came back to Japan and make systems for the electrochemistry system. But he works on the biochemistry, black lipid membrane, how to through the sodium and calcium ions to, so they don't need a potential stat because of the high impedance. But in the case of the electrochemistry, it's a very tough work to measure without the potential stat to the Fourier transformation system. So I just started at that time, but with mini computers. But anyway, that idea is just coming to, and recently, such kinds of the equivalent circuit ideas to get the immediate Fourier transformation technology is a very, very easier for us to detect of the inside of the electrode or inside of the electrode. So we try to the circuit equivalent for the commercially available lithium-ion batteries. But it's a little bit older batteries from the Panasonic. And then this is the equivalent circuit, but at that time, usual shape is coming to here, so we cannot fitting the experimental data with fitting. So we just thinking and discussing with the production companies. At that time, they combined the two particle size of the cathode materials, and also we should consider the SEI. So then assume such kinds of the equivalent circuit part, then the fitting becomes so nicely. So we just starting these ideas at that time. Then finally, also, previous one is a carbon anode, but this one is titanium oxide, lithium titanium oxide, anode. From this material comes from the Toshiba because SEIB the continuously longer, but the capacity is smaller. But in that cases, so we measured the same technology, but cyclability is just more than 5,000. The usual one is around here. In that cases, we can measure, this is just separating the square root of the cycle. So this one is just 1,000 around here. And so the usual lithium-ion batteries using the carbon anode cannot see the changing of the these shapes. Usually the cathode is just stop here, and energy, so the durability is just stop that because the cathode is just the same behavior, but anode is just stopped here. So the same technology can use this one, even the longer one, and the cathode is just showing to the changing the behavior. So this technology can be applied to any types of the lithium-ion batteries. So, and also one more interesting point is that this is the resistance or impedance in the inside of the electrode. Usually long time ago, 10 years ago, the impedance is 0.1 or several point something. But the recent one is coming to 10 to minus 1 ohm, or the less than milliohm order, which means cannot use the potential static control. So have to change the current response control. So we just going to the current response too. And also the battery monitoring system is always have a switch. And so the usual impedance is just using the sinusoidal one and measure data processing, they measure the results. But in that cases, we need always the apparatus. So very expensive. So when we use the squares, this is just on off. But in that case, we don't need apparatus of the sinusoidal one. And then the Fourier transformation, then the result is coming. And the lower than 1 hertz is sometimes very tough work to combine the sinusoidal from the pulse. So then we just the ideas or the square potential EIS to approve the possibilities. And so the Ferro-Ferri system is just get the same result with the same FRA. So that we try to the square current EIS, without FRA. And this one is a very important thing to the larger current batteries. So we try to the larger one. This one is comes from the Toshiba's SEIB, and totally the cell is 720 cells. So the one cell can be measured by this technologies. So we try to module and the cubicle and the systems, and the final one, the balancing in the 33 kilowatt hours to measure by the current systems. And so usually the frequency systems without the sinusoidal one is generally by the FRA. But without this one, only use the square pulses and also the current pulses, we can measure the total impedance. So becomes simpler. So usually the battery managing system contains the power controller. So this is just becomes a signal on. So we just made it, these systems. Then finally, time might be, sorry, I will quick up. And then this is the, two module systems, check it. And this one is without deteriorated module and with degraded or the deteriorated module. This is just the differences comes so larger. This is 0, this is 0 for this one. And so the deteriorated module is just moving to, and also the low frequency is so bigger. So difference is so bigger. So very easy find out. And for example, this is a 1, 2, 3, 4, 5, 6 module, and the same one, the total one is coming here, but one module is a bad one. This one is so moved to one frequency regions. Then the total of this one is just changing such kinds of the differences. So from the point of the industry, so check the module, or if the some degraded cell is inside of the module, can take off and change it. So this system can be applied to even the bigger module and also the bigger sizes of the systems. So we proved it. And also some companies are just trying to these technologies. And also this one is just watching to the automobile system too. And also another trial of this one is just supporting from the Saitama prefecture next door of our Tokyo, because we have a campus in the Saitama, and the Saitama prefecture is the support of the big foundation. At that time, we collaborated together with the Mitsubishi Electrics and to how to promote the support of the stable batteries.
Waseda University has developed an electrochemical impedance method to detect battery status. This detection method does not destroy the battery and can be used as an on-the-fly inspection method. It allows the defective points to be identified in the secondary battery. This community energy management system, CEMS, provides a detection method, the first of its kind in the world. This makes it possible to use the secondary battery for twice as long by controlling the charging and discharging process suited for each storage battery based on the detection results. This will lead to reduced battery costs, including running costs. In tests, we have been able to achieve integrated control of batteries from different manufacturers and with differing specifications. CEMS has allowed for the creation of a battery change schedule and the supply of new battery units. We have successfully developed a system with CEMS that is unprecedented in the world and has the potential to convert existing towns into eco-towns. Moreover, CEMS also offers the function of demand response that communicates with big electric companies using a highly versatile, globally standard protocol called OpenADR 2.0b. The Saitama launch of CEMS promotes the effective use of electric power in a community and converts existing towns into eco-towns.
So we just collaborated with the Mitsubishi Electrics, and we succeeded. And the Mitsubishi Electrics is proud of it. But the prices of the system are a little bit expensive, so we need the more advanced the systems too. And also, recently we just built up the center bill just like this. Oops. And so keeping this one to the 5 floors, and also the support is mainly from the government, and also gathered from the companies too. So we just enjoying to the building of the, we just shortly say the battery building, but it works, and it contains from the materials to finally the systems to this one. So that we just working for the materials and the production factory, and also advanced battery diagnosis system, the final system checks. So the total one is very encouraging to this industry. So that we collaborate recently the Toyota and also Panasonic and also Toshiba, and recently joined together over the German companies too. So that we enjoyed it very much. And so maybe the final one, the biosensors and the biomaterials. And we worked for the field emission FET based biosensors, but it's a rapid and simple, but not succeeded yet so well, because the experimental easier, but the first trial is very expensive one. But so we tried to this one to if they're going to the industry, the cost is cheaper, but the first performance is very expensive. So, but we collaborate together and also collaborated some companies, so that we doing that. And finally, this biosensors is convenient to connect to the cellular phones too. So anyway, we just started the micropiece sensors. One is a reference. The other one actually went to the checkers. At that time, we succeeded a small one with the companies, but unfortunately, the Horiba company is just refused it to the industrialization, because at that time, the field or the amount of the total one is only the $50 million US in the world, so cannot do the apply to the industrialization. So that they stop. The prototype is okay, but they stop it. So that we just changing the ideas to the biosensors, and also at that gate is just sensitive to the molecules. So that we attaching is just glutaraldehyde together, and also some is amino silane is just attached to the CO2. And then such kind of idea is just can possible in future. The environmental safety and behaviors are such kinds of the ideas. So then recently we focus on the mental stress management, because this one is targeted very usually the 5 or 7, but the cortisol or the amylase and also the IgA is the most important things to checking the stress recently. And the most important is the cortisol. So that we just focus on this target. And unfortunately, the cortisol doesn't have the charges of the molecule. So that we just use the aptamers. Aptamers is just combined together of the cortisol or something, then the charge is coming. And aptamer is just DNA nucleic acid artificial one. So the very, very stable. So this is so stable if compared to the enzyme. So that we just try to the aptamer, and amylase is okay, but the cortisol still needs a more higher sensitivity. IgA is okay. So finally, we are now, so the amylase and IgA is almost better, but still need the cortisol, the sensitivities. So that we collaborate together with the NEC's aptamers groups, and they created a new aptamers that it 100 times higher sensitivities. So that we are now going around here to moving this sensitivity. And also the allergy is possible to this system. So we just build up the communication schemes depending on the use. So several types, and And this one.
In our laboratory, we can detect the influenza virus and biomarkers by using the FAT biosensor. Using a Bluetooth wireless unit, we made a system that outputs the measurement results of FAT biosensor to smartphones. It can be checked easily and quickly by using the smartphone, even though it is far from the sampling point by using the wireless.
Yeah, this system is cheaper because colleagues of ours is just creating the venture business and very cheaper they succeeded. And also I cut off this one. So recently we just using instead of the bread, to use the toothbrush types to make it. And then this is just the final target to each independent people to get the information on the mental stress systems. So in futures, we hope to combine this, the toothbrushes type of sensors, and then directly coming to the information through the cellular phones to the doctors. I think this system can combine together of the Bitcoin or something like blockchain systems. So that we are also starting together with the discussion of that groups, Jewish groups. So that we just if succeeded of such kind of system and combine together of the cellular phone, the field of the sensor is grown up. So I just thinking to such kinds of the next trials. And the conclusions is just academic side, the selection of the new topics is very important for the young student. Young student, if interested to that targets, they never sleep and they can working even Sunday. So that is so important thing to the young people. And also passion to the new field is also very important. At that time, collaboration together of the industry. So we never assist the lights from the academic side, but for the industry side. Give, and sometimes a little bit comes. Then that is the most important collaboration concept, I think. And also the favorite motto of the recent one is Japanese, is Sokuten Kyoshi, but it's just translated to English. Listen to the nature and follow the heaven. This is our same ideas of the, man, someone knows well. So the very important thing is listen to the nature and follow the heaven, that they just get the information from directly to the next step. And also, we are very happy to the young people. Young people is just watching and found out the good things. Then we succeed so well. And also thanks to the families to the working freely to such kind of the items. So this is my conclusion. Thank you very much.